Okay, so welcome everybody to our talk today. We are going to talk about Scotty, which is our solution for efficient window aggregation for your stream processing system, or in general for stream processing systems. Let me give you a brief introduction about our background. So we are both researchers from TU Berlin. And my name is Jonas, this is Philipp, who will do this talk jointly with me. And we are from the Database Systems and Information Management Research Group at TU Berlin. So for those who don't know us, this is the group which is the origin, for example, of Apache Flink or the Emma language. And we are doing quite some research in different areas, of course on core database systems, but recently a lot about stream processing, information management, the machine learning aspects of that, and basically all the systems research which in the end powers database systems and machine learning use cases. So today we are heavily focusing on stream processing systems, so I want to start with a very brief introduction to tell what's the major difference between maybe your batch processing engine and a stream processing system, since this is the foundation to understand this deep dive we are going to do into one particular operator we are tuning, which is the windowing and aggregation operator. So what you see on this slide is a figure I took from one of the most popular textbooks in databases and stream processing. And what you basically have in a streaming engine is you have several input streams here shown on the left-hand side. You have a processor and you have output streams. So usually you are considering a limited working storage. So this is the state of operations or so you can keep in memory. And you have some archival storage, which could be your Amazon S3 or any other hard drive or whatever storage you connect to your system. And what you know from relational databases, big queries, things like this, is ad hoc queries, which means that you submit a query once, you get an answer for that query, and then the query is done. What we look into is something which is special for stream processing engines, and those are the standing queries. The difference for standing queries is that they are designed to be long-running, potentially months or years, so they continuously consume input data, do something with that data, and then produce outputs. So let's dive a bit into those standing queries. So what we have is a stream processing pipeline, and this stream processing pipeline, since it should continuously produce outputs, is a series of concurrently running operators. So we have a stream of data which flows through those operators, and of course, in order to make some reason about our data or to compute some results, we need to kind of make the relation between those different data points. And one operator here we are looking into today is the window aggregation operator, which is kind of key for analyzing data streams. So what this operator does is it basically accumulates values, here the values 5 and 3, then it computes some aggregation, here it just computes a sum, the aggregate 8, and this will then be our output. But of course in practice those aggregation functions can be way more complex, not only arithmetic operations like sum, minimum, maximum, etc. But of course we also have statistics, we have analysis where we want to have, let's say, daily or monthly statistics, where we want to have sliding aggregations, we maybe want to have samples from our data stream using reservoir sampling, maybe look into things like Bloom filters and so on. And of course we also have maybe in the background machine learning models which we want to update, so we have those ML model updates and things like concept drift detections when we want to see that, for example, the behavior of a user changed, the interests of a user changed, the way users are interacting with our product changed, and so on and so forth. So all these complex use cases are something which you can do with a more complex aggregation function over a sliding time window. But in order to have a good explanation, we do this today mostly with a sum aggregation to basically break it down to something which one can easily follow in such a presentation. So the some performance numbers you see, and a lot of the work we have done is based on Apache Flink, which is an engine for stateful stream processing, and of course it's open source. And if you basically look on the figure which you find basically on the architecture page of the Flink website, then you can see that this figure also very well relates to what we have seen as a stream processing system on the introductory slides. So on the left-hand side, you have many data sources which you can interpret as input streams or just as storage, which you can read in a streaming fashion. You then have event-driven application streaming pipelines, analytics tasks, and also down there you have all the archival storage solutions like HDFS, S3, and so on and so forth, and all the output connectors to write to databases, to write output streams, and so on. So this is the background we have, and from that we basically came to the motivation for this research project. So our motivation came basically from looking at the Jira tasks which were opened, or user requests which were opened for the Flink open source projects. And there we had things like here poor performance with sliding windows, or people asking to improve the sliding window performance. And if we look in the description of one of those requests, we can actually understand the problem, because someone wanted to compute a window for the time of 10 minutes, which slides by 1 second. So every second there should be an aggregate for the last 10 minutes. And if you look how this is implemented in Apache Beam, which runs on Google Cloud Dataflow, and how this is implemented in Apache Flink, each individual window is an individual bucket. So any item or any tuple you receive will be aggregated in that bucket for each window it belongs to, which means in this example there are 600 concurrent windows, so each tuple is processed 600 times by each window, which has an overlap, and of course this is quite suboptimal, and one should be able to improve that to get a way higher throughput, or just to pay less because you can provision a smaller cluster. So we have done quite some research on that, and I want to give you a brief overview about that background. So everything started with the Scotty paper, where we looked mostly in the expressiveness with respect to window types. So of course you can not only have sliding windows which switch by a different or move by a different time range, but there's way more complex things you want to do, like having a window per user session, or having different time measures, like for example having a window for kilometers driven by a car rather than a time window, or having a window based on tuple counts. And here we have a more like general solution which describes how to handle all those window types. Then we had a Scotty paper where we mostly looked, in addition to that, to out of order processing. What is if we have late events and need to update or maintain our results in a correct way, and also how do we optimize that for session windows if we have a lot of user sessions in the system. And last but not least, this is basically this year's publication, which brings everything together, where we basically looked in all the different workload characteristics you can have, and then designed a solution which dynamically adapts to the workload, so to the queries you submit to the system, in order to get the most optimal performance. And this is now open source in what we call the Scotty window processor. And I invite you to check it out on the GitHub repository, and I will also later bring up the QR code again so that you can have enough time to take photos for that. So to give you a brief introduction about the technique, I want to talk about stream slicing, which is the foundational technique on which we build this Scotty solution. And I will first do that with an example which in general describes stream slicing with very simple sliding windows, and then I will go a bit into the workload characteristics and how they impact the slicing logic and why that is a challenge. So the first thing about slicing is the key idea that we not have a bucket per window, but instead here we have 3 windows which are just sliced by or shifted by a certain time. What we say is every time a window in the system starts or a window ends, we also start a new slice, which means that the number of slices depends on our workload, which then again means that we can quite well plan, depending on the workload we submit to the system, how much memory we need in order to store those slices. We then have an incremental computation which overcomes the throughput limit I pointed out in the issue before. So let's say the first tuple arrives, here it is the value 7, then the next tuple arrives, it is the value 5, and the nice thing here is that now we can compute an incremental aggregate, so for the sum aggregation we can compute the value 12, and only this value we need to store in that slice. And this value we can continuously update, which means that we store the partial aggregates instead of all the tuples, if that is possible, and we have a small memory footprint, so a small state size per slice. What's also very important to see here is that if this, as the stream continues, each individual tuple gets not assigned to all the buckets which would have been there to represent the windows, but it gets assigned to exactly one slice. So we avoid this 600 times repetition I introduced in the issue description in the beginning. And then when the window ends, what we basically need to do is we need to compute a final aggregation, and this we do for this example here by aggregating the partial results for our slices. Here it's the value 18, 11, and 6 to the value 35. And the nice thing here is that this we can do with a quite low latency, because we just require a few aggregation steps. Maybe if you have a lot of girls in the system, there might be a few hundred of slices, but those you can update very fast with the final aggregation for those you can do very fast with low latency, and you could even have a tree structure with pre-aggregates to have even lower latency for that, so that this will not become your bottleneck. So now let's look into how it became more complex if we look into the workload characteristics, which is the core part of the latest paper I pointed out before. So here we looked into all the different things which can be part of your stream processing query, and the first thing which can differ a lot, of course, is your aggregation function. So you can just look into the mathematical properties and say, is this function associative, is it commutative, is it invertible? But also in the basically memory requirement, is it distributive, algebraic, holistic, and depending on what kind of aggregation function you use, you enable the system to perform quite different optimizations. We also can look into the window types. The examples I showed so far, they are just context-free windows, which means I can tell exactly when each window will start and end from the beginning without looking at any data. But of course, there are also context-aware windows like session windows or windows where you want to react on certain deltas between values in your input stream. So those are context-aware windows, which then require different optimizations again. We have the window measures, which I mentioned before, like time, tuple count, or anything arbitrary, like let's say an increasing transaction ID in your database. And of course, we have the stream order, where your stream can be either in order or out of order. And if you can label the stream that you will only expect in order tuples, or it is okay to drop late events, then of course we can perform additional optimizations. So the nice thing about the Scotty window processor is that we basically have one general solution which combines the generality of more complex techniques which are less performant with the efficiency of the slicing optimizations in a single solution. And I want to give you one more example here which illustrates a bit more what's the impact of those workload characteristics I mentioned on these slides. So let's first look at an example, and I bring up some stream with random numbers here, and let's say we submit a query where we just want to have a tumbling, so a non-overlapping window with a length of 5 tuples. Length of 5 tuples means I now have a window measure which is a tuple count, so the timestamps in that sense of my values will just be the sequence ID here counted from 1 to 15. So in the next step, we know that since we only have one query, the windows in this example are exactly the slices, so we can compute the partial aggregates, which are 11, 13, and 12, and this is basically how this is represented in slices. So now the first question would be, but what if this stream is out of order? And there we briefly need to think about how is stream order actually defined. So stream order is defined by the event time, so the time when actually a value was captured at the data source, which means that each of those tuples would also have a timestamp. And these timestamps define the order in which we should enumerate the tuple for the count-based window. So now the system can receive an out-of-order tuple here with the value 5 and the timestamp, event timestamp 49. And now we actually have a problem because we need to update those aggregates. So what we need to be able to do if we have a count-based window plus out-of-order tuples is that we need to be able to shift those and to move in the value 5 and then to update our results or to make sure that we produce correct results. So in this case, what we can do is we can update those two slices. And since we knew that we have a query with a count-based window, the Scotty window processor would have known that we need to also keep the individual tuples in order to be able to perform that update. So here we can do an incremental update, moving the 5 here, and then computing 5 plus 13 minus 3, and 3 plus 12 minus 1. So this is all fine as long as your aggregation function is invertible, so the plus you can easily do the minus and thereby shift the results as needed. But what if the aggregation function is not invertible? And I will keep it with the example at this point, but if you look in the paper I linked before, what we actually provide is all the decision trees where you can see, depending on the different workload characteristics, how does that impact the way the Scotty window processor behaves and how does this impact the way the system performs. So with that, I want to stop the introduction with the examples and I want to hand over to Philipp and he will give you a bit more of an introduction about the Scotty window processor itself and the coding backgrounds for that.
Exactly. Thanks. So what we provide to you is basically the window operator, which you can then embed into your Flink, Beam, Storm pipeline, or basically whatever stream processing system you have. And this enables you to just define your workload, to implement your window functions and everything, and just benefit from the efficient computations Scotty offers. So you basically don't have to think about all the different decisions, like if tuples have to be inserted or not. Scotty will figure out the most efficient way for you to compute your window aggregates depending on your workload. So let's start basically with the key features of Scotty. So it's one window operator, which is independent of any system. So you don't have to use Flink, you can just embed it. You can also just use it without any stream processing system and just embed it in your standard Java application. It enables you or gives you high performance window aggregations with the stream slicing technique and scales to thousands of concurrent windows. So for example, with the sliding window example from before, it doesn't matter anymore how much overlap you have in your sliding window definition. It will just result in the same throughput always. And even you can share these aggregates across multiple windows. For example, when you have a stream and you want to process a tumbling window over 1 minute and then over an hour and then over a day, you can share these aggregates and will have always the same performance. And this is really useful when you want, for example, to detect patterns where you maybe need multiple aggregates of different time scales. And furthermore, Scotty, or the window processor, gives you the freedom of all the workload characteristics we discussed before, like the different window types, the aggregation functions, the window measures, and it's also independent of the order of your stream. And we already provide you connectors to Flink, Beam, and Storm, and we are currently also implementing more connectors where we want to bring Scotty directly to Google Dataflow, and which will you then enable to have more efficient stream processing on Google Dataflow, which in the end will save you some money. So let's dive more deep into the architecture. So you have on left side your input stream, which is consumed by the window operator, which maintains the stream slices and computes the window aggregates. For doing so, you basically define window aggregation requests, which consists of the windowing function, the window measure, and the window type. And depending on this information, we can, or Scotty will, determine if, for example, tuples can have to be kept or can be dropped to improve efficiency. What is also interesting is that you could exchange the window definitions at runtime. For example, that you can have two streams, one with the input data and one with the definitions, and you have basically a dynamic windowing engine. And in the end, based on this information, Scotty performs your window aggregates and gives you the results. To extend the Scotty operator and to introduce own aggregation functions and window types, we have an interface which you can just implement and which abstracts the details of these different decisions. So Scotty basically combines the generality and the efficiency in one single solution. So let's look at some benchmark examples. For example, here we scale the number of concurrent windows for a sliding window, and basically scale the overlap in a sliding window. And what we see, Flink basically outperforms Storm and Beam with a quite high factor and reaches nearly 2 million, around 2 million tuples at a second. However, when we now increase this overlap, we see that the performance of Flink drastically drops. Only the performance of Storm is constant because it uses a different implementation of the window operator. However, the throughput of Storm is also really low. When we now introduce Scotty, we see that first of all, the throughput of all systems is independent of the number of concurrent windows. Okay, we wanted to achieve this. But also the throughput of like Storm and Beam is now much higher because we can basically share these pre-aggregates and have a much more efficient solution. So how can you use Scotty? You basically clone the repository and make a Maven install to use it as a dependency in your normal Flink pipeline. It could also be a Beam pipeline or a Storm, that doesn't matter. It's basically the same for all systems. Then you have to basically create this Scotty window operator and initialize it with the aggregation function you want to have. You could also add multiple aggregation functions. That's completely up to you. Then you can define or add multiple window definitions. For example, here a tumbling window, a session window, and a sliding window, all on the same window operator, that you can really share all the aggregations across these different windows. And finally, you add basically the window operator to your normal stream processing pipeline. So in Flink, you would just exchange the call to the standard window operator with a processing function which consumes our window operator. So you don't have to change a lot on your stream processing pipeline. And what is also interesting is that the definition of this aggregation functions is completely independent now of your stream processing system. You could just have implemented your aggregation functions one time with our framework and execute it in a pipeline for Beam or in a pipeline for Flink. So this now also gets independent. And to implement your own aggregation function, you basically have to implement three functions, which is lift, combine, and lower. So lift is the first stage, which basically consumes one of your input tuples from the stream and converts it to one of the partial aggregates, which is then combined with the partial aggregate which is already stored in a slice. And finally, when you want then to convert or create the output of a window aggregate, the lower function is called. So let me show you one example. For example, when we have an average, we store only the sum and the count, because when we divide the sum by the count, we have the average. So the sum and the count are the partials we store in a slice. So let me show you this. This is basically our initial state. We have an input stream, and we have now already a partial with a sum of 3 and a count also of 3. And when we now send the next tuple to our window operator, we first lift this tuple to a 5, well, the tuple is a 5, the value, and a 1. And then we combine this with our partial aggregate. So we calculate the sum of the 5 and the 3, or 8, and sum of, well, introduce the sum of the count. And then finally, to calculate the window aggregate, we call the lower function, which does the division in the end. So when you just implement the 3 functions, you can basically introduce new aggregation functions to Scotty and then benefit from all the pre-aggregation sharing of Scotty and the performance benefits. So to wrap up, Jonas will now present some of our different current projects we have in our research group. And yeah.
Yeah, so as I said in the beginning, we are a research group, and of course this research never stops. So we have some upcoming research projects I want to briefly mention to first outline our vision on how does the stream processing thing continue and what are the next things which are up for investigation on our side. So one thing what we are looking at and what we published last month is the idea of the Nebula Stream Platform, which brings the idea of those stream processing use cases and the efficient window aggregation to the IoT age, basically combining a cloud layer with the fog layer, where you basically want to do computations on edge devices as much as possible in one unique system, which from the user perspective looks like basically one database or one streaming engine, but it incubates all the different edge devices, like for example your smartphones or your home automation devices. So if you are interested in that, the slides will be online afterwards, and I invite you to check out this vision paper on Archive. And another thing what we are looking at on a different level is the Agora platform, where we are interested in checking out open ecosystems for democratizing data science and artificial intelligence. So here we are really looking into basically a Lego-like ecosystem where you can flexibly combine different stream processing engines with different algorithms, with different data sets, and you have some trading mechanism plus the native execution engine you can run on different platforms. So I also invite you to check this on the recent Archive publication. And of course, why am I telling you this? Of course, we are hiring. We are hiring research associates, PhD students, and postdocs. So if you know someone who may be interested, or if you are interested yourself, then please reach out to us after the talk, or just send a mail to our job task ID or to one of us. Don't make a big formal application, just write a few sentences about you and that you may be interested, or that you know someone who may be interested, and then we can get in touch and have a chat about what we can offer and why it's cool to be a member of a research group. So to wrap up the talk, let me summarize the Scotty features and also explicitly point out what's the roadmap for the Scotty window processor. So we presented basically one window operator which works for many systems. A key idea here is to prevent the duplicated work in all the open source projects and have the vision of one project which has this key streaming feature in a very efficient way. We believe that stream slicing is the right way to do this because we have a combination of high performance with terms of throughput, but we also have a solution which we can quite well manage with state backends. And we have the possibility here to scale to thousands of concurrent windows and to share the aggregates if we have multiple queries in the system. We have, for now, 3 connectors implemented. If you look in the open source project, it's actually not too hard to add a new connector. It's basically just that so far we didn't have the time to spend on implementing basically all the stream processing engines here as a connector. So of course contributions to that project are highly welcome. We are also very happy if someone wants to test this in a production environment or in a company and want to bring up a project saying, let's see if we can save money using that, or let's see if we can make our pipelines easier, if we can basically merge several processing pipelines into one pipeline, because we can have several windows in one, or window specifications in one operator, and so on and so forth. And I think with that we are at the end of that talk, and I'm happy to take your questions. Yes.
Apache Flink can, you can use the Apache Flink runner to run Apache Bean in Flink, and this Scotty window that you created can be used in this runner. But can you run it in Dataflow?
Yeah, basically that's right. You can. We just have a connector to Apache Beam, so it's basically then just a operator in your normal Beam pipeline. So it's independent of the runner which is running under it. So it would also be possible to run it on Dataflow. We have not done any experiments with that yet, but it's on our roadmap to do so. But we would also be happy when somebody else tries it out.
Yeah,
So if you do it, drop us a mail or something, so that we know we don't need to replicate work. So anything we have done, we can share with you, and of course we would be highly interested in what's the result.
There's an email from me like in 6 months or something.
Thanks.
Perfect.
Yeah.
Yeah, first of all, thanks for the talk, it was really interesting. So my question would be regarding the performance data that you show for, I think, the Flink use case. When you go from the one parallel window function which maintains all the tunnels itself to the slicing approach, do you see a decrease in traffic for just one single not parallel window?
So this benchmark was basically on a single key with a parallelism of 1. So it's just not parallelized. But I mean, in Flink, you parallelize because you have multiple keys, and then Flink can split or distribute the different keys on your cluster, basically. And then when you would now introduce Scotty, then on every node you would have one Scotty operator, which will be much more efficient. So we did also some experiments with this and saw basically that in every case the Scotty window operator is more efficient than the standard Flink operator, even when you scale it across multiple machines.
So what you need to keep in mind is that for all those engines mentioned here, they all parallelize by key partitioning, which means that if you have a heavy hitter key and you cannot distribute within that key, you basically need one very powerful machine to take care of this. Or you need some way to make your keys more distributed and to somehow manipulate the keys. So that's not solved here. But what you have in your cluster is that since you can do several window operations in one operator, you see a lower network utilization, because the data only goes to one node which does the windowing for, let's say, 3, 5, 10, however many you have window specifications, and then all the aggregations get out from there. While in a different use case, you would have 5 window operators per key, and you would also have the data replicated for each of those window operators. So there of course, you see a reduction on the input side by, if you have 5 windows, by a factor of 5, right? Because you would have that split operation which basically replicates your data. Further questions?
No, I don't think so.
Okay, then thank you very much for being here, and I wish you a nice time at the party later and at the rest of Code Talks.